start kori. So welcome back. So if you just go to the end of the last week's topic, we have discussed a couple of retro quiz or different kind of question answers based on very preliminary retrosynthetic disconnection. I hope that you have gone through it and probably you will be able to solve it. So in continuation with the earlier one, let us talk about something similar kind of problem which will basically give you a flavor that what kind of problems we will be dealing throughout this entire coursework. So next one, as you see, we have chosen a particular compound which is very simple, is a anisetic acid, orthoanisetic acid, means 2-methoxybenzoic acid. Now this compound was given you as a target and the starting material I have given. So starting material is basically what I am looking for is anisole, orthomethoxybenzene. Now so this is your target molecule, the left hand side, and this is your starting material or the precursor. In principle you can do it by numerous transformations, and I am just trying to figure it out what are the transformations you can think about. Probably all of you know it, the very popular Vilsmeier-Hack reaction. So what this will give? Vilsmeier-Hack reaction will be giving a aldehyde functionality at the ortho as well as para position. So we have a regiochemical issue, and that is a bit serious concern because we are only dealing with a single product. So regiochemistry we are not going to talk, and so probably you can think about something very interesting transformation which I am not sure whether you are aware of that, but we will be talking about some reaction which is named as lateral lithiation. Now what is that? I said when you are having a anisole as a compound and you subject this anisole with a base. Now normally we use base something like secondary butyl lithium or sec butyl lithium, and OMe group is basically electron withdrawing group, and that is why the orthohydrogens seems to be little bit acidic when they are attached to a vinylic or aryl system. And eventually if you subject this compound with sec butyl lithium or tertiary butyl lithium, you expect that one of these orthohydrogen will be removed and you get a lithiated species, and that is called lateral lithiation or ortholithiation. Now the main point is ortho group is in close proximity with the O-methoxy group, that is why the hydrogen ortho to the O-methoxy group has much more kinetic acidity, and that is why it is been picked up. Now this compound is basically nothing, you can simply write it this compound as a this minus and lithium plus. Now depending on the target which was given to you, you can basically now quench it with different electrophile. For this case, in our parent case, we will be treating this compound with carbon dioxide as an electrophile, and you will find that after usual acidic workup you will be getting anisetic acid as a main product. On the contrary, you can do a different kind of electrophilic trapping. Let us say for instances, if you use dimethyl formamide as a electrophile, this case is this minus will come here, attack these things, and finally you will get a aldehyde as a main product, orthomethoxyanisaldehyd. Now this particular lateral lithiation is very unique transformation, and it will basically help you to functionalize aromatic nucleus when a electron withdrawing groups like electron withdrawing group I say mainly O-methoxy, NMe2 or NR2, those kind of groups, CO2ET, CO2H, those are essentially required to activate the aromatic nucleus, and then you can do a lateral lithiation. This chemistry was first pioneered or explored by Professor Peter Bick, that is called Bick lithiation, Peter Bick is called big lithiation, and that is a very interesting transformation. So, we have just given the same thing through a retro arrow in the overall PowerPoint slide, and we will find that this is our main target molecule. So, coming to the next quiz or similar kind of quiz, we will next talk about a little bit of a different molecule, a molecule which I am now next going to be write it down. You will see in it the structure here is basically a cyclohexane based compound, and if you see a close structural view in this compound, you will find there are two functional groups attached. It is basically a secondary hydroxy as well as you have a primary hydroxy. So, both the groups are there, okay. And the target molecule which was given to you is this one, and the starting precursor or the starting material was a cyclohexene based carboxylaldehyde. Now, definitely the starting material was chosen very judiciously. So, you need to know certain transformation to carry out this kind of functional group interconversion. So, now go back to the retro. So, draw a retro arrow like this, and then you can basically find it out. The first step will be a functional group addition, and if you have access of this kind of compound which is basically nothing a cyclic ester, then you can just do a reductive cleavage with lithium aluminum hydride kind of reagent that will basically lead to this diol. This is a functional group addition reaction, or you can say is a functional group interconversion. So, these names are basically just to give you a flavor. Is in principle FGA, FGI are kind of similar, fine. So, once you have this anhydride which you can cleave it, now next question is how to access this anhydride, fine. The next retro, see it very carefully. We have put a halides group or specifically iodo group to introduce or to bring the olefinic unsaturation in the given target molecule. The given target molecule is having a olefinic unsaturation. So, what we trying to do the retro, sometimes this kind of disconnection was used. You which bond you want to disconnect, you put a dotted line, and based on that you put a bold line. This is called the retrosynthetic pathway to design that which bond to disconnect. So, this way this bond will be making this pi bond, and how you can make this pi bond? If you have a iodo and you have a hydrogen here, you will basically doing a simple E2 elimination by a FGI or even FGA, fine. Now, the next question will be asking that why and where from you have to make this iodolactone. This compound is nothing, is a iodolactone, is a iodolactone, okay. So, this iodolactone essentially can be made by a very simple transformation which we will be now talking about, is called iodolactonization. And now you can just try to correlate the starting material is almost similar, you just now need a functional group interconversion. So, this is your starting material, you basically do a oxidative transformation here to convert it to corresponding carboxylic acid. Now, here once this carboxylic acid you are having, now it will be doing the forward path. When you are having this corresponding carboxylic acid, you keep it, you put a or you subject it this carboxylic acid with iodine and sodium bicarbonate. Now, what happen? You are using sodium bicarbonate, that basically will make a carboxylate salt or C double bond O minus, and as this iodine is there, you are trying to have a iodonium ion. So, this bond will be loose, cyclic iodonium ion. Now, this iodonium ion, as you all know, it will be internally attacked by a nucleophile, and here O minus is basically attacking to this carbon, and then you will be getting this O, C double bond O and iodine here. So, in principle this is the main reaction which dictates that the synthetic pathway is very much viable, and this kind of reactions are often regarded as a halolactonization. Halo means any halogen species you can use as a electrophile, halolactonization. So, if you use X equal to chloro, it is called chlorolactonization. If you use X equal to bromo, it is called bromolactonization. If you use iodo, you can use you can call this iodolactonization. Normally we prefer iodo because as we know that next step is a elimination reaction, and iodine compounds are good leaving group. So, they can follow the subsequent pathway. So, your next path is absolutely fine. Now, you can do a simple elimination by standard base. The base basically you can use any non-nucleophilic bases. The preferred base are DBU or DAPCO, which are basically sterically bulky non-nucleophilic base. I am just telling you the name DBU and DAPCO, try to get their correct structure from many sources. DBU stands for diazabicycloandesine, DAPCO is diazabicyclooctane. They are having a bicyclic nitrogen framework, which are basically sterically bulky non-nucleophilic bases, and once you have this, that basically give you this initial intermediate, and then you can do a LH mediated reductive cleavage that will basically give you the target diol. So, this is this kind of synthetic pathway is very efficient, very eventually the starting material, this cyclohexene carboxylate is cheap. The only thing is, if you know the iodolactonization method, I am sure you will be able to do it, and that basically gives you the entire pathway. Fine. So, coming to the another quiz based on similar thing. Now, first follow the slide. What kind of structure was there for the target molecule? The target molecule basically having a cyclopentane structure as a core framework, and now we will try to explain certain terminologies which I have already explained earlier. Now, see, I said that this molecule is a cyclopentane framework having a this long appendage. Now, appendage means basically a hanging group. Now, this appendage also contains a functional group. It is having a secondary alcohol functionality and is having a CH2 pH as a alkyl chain. The starting material which was given is pretty interesting, a cyclohexene which was given to you as a starting material. So, now you need to think that what kind of reaction you will be doing, so that parent cyclohexene ring will undergo a ring contraction to give a one member less cyclopentane. For that things we need to find it out. I do not know whether you will be familiar with couple of I mean some interesting name reactions, but nevertheless we will do the retro. We will do the retro first. Follow the standard pathway of retro. What we did? We basically did a this kind of retro, and we say that if you having this aldehyde, simple cyclopentane carboxyldehyde with this Grignard, we said MgX and pH. So, pH CH2 MgX. So, it is basically Grignard acting as a nucleophile to a electrophilic aldehyde. That was very simple. Okay. Now, the next step which was bit crucial, not bit crucial, it is absolutely crucial. This Grignard is you can easily prepare from corresponding bromo compound. You take the corresponding bromide, heat with simple magnesium 0, magnesium metal. Now, this particular compound cyclopentane carboxyldehyde, in principle or in reality it can be accessed through a cyclohexene based epoxide through a rearrangement. It is named as semi-pinacolon rearrangement or a Manual type of rearrangement. Manual is a name reaction, and this is the key transformation we are looking for. Now, what exactly it is? When you have a cyclohexene epoxide, you treat with a Lewis acid. Lewis acid mainly you can take any Lewis acid. The preferred Lewis acid will take BF3 ethylate. For sake of simplicity, we will just put it as a Lewis acid. Now, Lewis acid will try to coordinate with these things, okay. And then you will find that once it coordinates, these carbon oxygen bonds are loosen up. Once this carbon oxygen bonds are loosened up or kind of fragile, it is a symmetrical epoxide. So, it will try to open up and will give you a carbonium ion here, and once this carbonium ion is generated, it basically undergoes a simple 1-2 migration, and that basically is the main factor to give you the corresponding. Once this basically migrates, you have a ring contracted product here, and then Lewis acid, basically Lewis acid will come back and give you the corresponding parent aldehyde. Now, once this parent aldehyde has been done, you do the corresponding reaction with magnesium turning, that will be giving you the corresponding Grignard. Even we can do a other reaction, you just do a metallic lithium exchange, lithium metal, which will basically give you corresponding lithiated species, which is also a good nucleophile, and then it can react to this corresponding aldehyde to yield you the product. So, here this kind of retro, essentially you can fit it out in this category, is a transformation based retro. Transformation, the main transformations we have talked here is a Menwald rearrangement. So, Menwald rearrangement is a synthetically very useful reaction when you have epoxide and you treat with Lewis acid. Now, here we have taken a symmetrical epoxide. There are examples where you can take unsymmetrical epoxide, and based on the initial carbocation forming, the rearrangement also will be taking place, and the rearrangement basically depends on the more stable carbocation which will be generated in the final reaction product. That will be the major outcome of the main reaction. Now, synthetically is very useful, and I have used a very simple Menwald rearrangement kind of reaction, which will give your main target as we discussed here. So, things we will just try to continue the similar kind of problem, but little bit difficult in the sense. Now, we have chosen a molecule which is having a bicyclic framework, and see its structure. It is a interesting structural features. If you look about its planar structure, it is kind of a symmetrical. You can have a nice plane of symmetry or mirror plane of symmetry through these two OH. As I said, you have to take a 2-dimensional structure. Fine. Now, the target molecule was this one, which is basically a dihydroxy compound and having a naphthalene framework. This naphthalene framework is a tetrahydronaphthalene framework, and the target was this one, and the starting precursor which was given to you is a naphthalene, simple naphthalene molecule, which is a cheap commercially available starting material. Now, if you closely analyze, the starting material is naphthalene, the final product is basically not aromatic. So, you have to do a de-aromatization reaction, and you have to destabilize the aromaticity of the naphthalene. Now, can you name some reactions where a aromatic nucleus has been converted to a non-aromatic compound? The very beginning reaction which should come to your mind is a Barch reduction. Barch reduction is principally very important reaction, and probably during subsequent coursework we will be talking this Barch reduction in very detail. Not only Barch reduction, when you do a Barch reduction, you will find this Barch reduction is a pretty important interesting reaction. I will try to do a simple Barch reduction of a benzene system. Basically, if you subject benzene with the sodium and liquid ammonia, the mechanism probably you can find it out, you get a this kind of compound. Now, if the benzene has been substituted with electron releasing group, what will be the product? If the benzene is substituted with electron donating group, what will be the product? That is, you just think it about that what will be the relative product. If the benzene is substituted with electron releasing group like O-methoxy, if it is substituted electron donating, electron withdrawing, it will be electron withdrawing group. One is electron releasing like O-methoxy, and electron withdrawing means CO2H kind of group. Then you have to predict the which kind of product will find formed, and that has a potential very good synthetic importance. Now, coming to the problem, initial target was the molecule which was drawn here. You have given naphthalene, so subject to sodium, ammonia or liquid ammonia, and then for naphthalene case you basically will get this kind of compound. Now, the compound which was initial intermediate is a triolefin, triolefin. Now, if you see that this olefins, the side olefin is disubstituted because you are having 2 hydrogens here. This side olefin having again disubstituted, but this middle olefin is basically tetrasubstituted. It does not have a hydrogen, basically more of electron rich, and that is why when you are doing a diol reaction or osmotic tetroxide reaction, dihydroxylation, and the point is you have to do a dihydroxylation reaction with 1 equivalent of osmium tetroxide, then you can absolutely control the geometry. Okay. Now, if you do a dihydroxylation, that basically do not give you the exact product, because here the relative geometries of OH and OH are anti to each other. OH1 and OH2 are basically anti or trans to each other. And as you know, the dihydroxylation often gives a cis diol. So, probably dihydroxylation will not be a viable pathway, as I said. So, you have to think about some alternative pathway. Do not worry, there are alternative pathways. So, what you do is subject to these things with a MCPBA, metachloroperbenzoic acid, do a corresponding epoxidation, and as this is a more electron rich olefin, electron deficient oxidizing species or electron deficient oxygen species will attack to electron rich species. So, once you get the MCPBA, epoxide opening will always give you anti-diol by the standard SN2 condition. So, that is pretty much known, and now you will get the product which is having anti geometry in the double bond. You can do a acid catalyzed cleavage, even you can do a base catalyzed cleavage also. So, that basically depending on your particular resources, you can do a either acid catalysis or base catalysis. If you do a base catalysis, means a stronger nucleophile, SN2 chances are very high, and in those cases normally you will get a always a anti-diol. So, that will solve the problem. So, the particular transformation which is required here is a, now is it transformation as a Birch reduction you require, and always also you require a epoxidation of a double bond by metachloroperbenzoic acid, and then epoxide cleavage. So, this is the main transformation which is used. Eventually, you can also say that the initial starting material does not have functional group, the final target having a dihydroxy or bis hydroxy functional group. So, it can be termed in that way also. Okay. So, next we will be trying to figure it out a little bit complex system, little bit complex. Let us figure out the structure. We have taken a cyclohexene based compound. If you see in the main lecture, this one, and here you are having a corresponding the starting material which was given to you a cyclohexenone, 3-methyl cyclohexenone. Do a close analysis. What are the groups are available to you? It's basically you are having a olefinic bond here, and you are having alpha beta unsaturated carbonyl. You are having a methyl. This methyl might be this methyl. Now, this is it. This compound you can try to figure it out in a alpha, beta, gamma, delta. Basically, this is alpha, beta, gamma, delta carbonyl compound. That was the functional group analysis, carbonyl compound. For this compound, this kind of compound, let us do a simple straightforward analysis. We will be doing this analysis. We know that if you can convert this ester, you can easily go back to the aldehyde by simple functional group addition. This is your target molecule, fine. Now, here your main trick comes, how you can prepare this gamma delta unsaturated ester. The reaction which we are looking for is basically a very important name reaction named as Johnson orthoester Claisen rearrangement. Johnson orthoester rearrangement. Probably in the next subsequent section we will talk about this rearrangement or this mechanism in detail. This mechanism we will be discussing in detail little bit later on. So, once you are having these starting materials, then you can do a Johnson orthoester rearrangement and exactly the reagent which is used here is trimethyl orthoacetate, and once you have this Johnson orthoester rearrangement, this you basically can be synthesized from this starting material by a Luce reduction. It is again a transformation. Now, what is Luce reduction? What is Johnson orthoester Claisen rearrangement? Probably we can discuss all those things in the next week. So, okay. So, again we will see you in the next week. Bye.